Welcome to On Chemistry. In this video, we are going to see Sharpless Asymmetric Epoxidation. It is an oxidation reaction from alkene. It is an important naming reaction. We will completely learn Sharpless Asymmetric Epoxidation with 25 fully solved examples. What is inside this video? At first, we will see what is Sharpless asymmetric epoxidation, then basics involved in that reaction, that includes mechanism, regioselectivity, and trick to find the final product, and library of examples. That is very important one because we are going to see 25 fully solved examples from various examinations. So stay tuned. At first, we are going to see the basics of Sharpless asymmetric epoxidation. First, let us see what is Sharpless asymmetric epoxidation. The reaction has starting material, which is allylic alcohol. Product is epoxide, that is oxidation happen on the alkene. You are using titanium isopropoxide and peroxide. Then you have control over the reaction through DET, plus DET and minus DET. That will decide below or above the plane reaction. It is the enantioselective synthesis, very important because of its stereochemical nature. The reagents involve big molecules. Better you know all the structures because sometimes questions are coming with structure. You have to guess whether it is plus DET or minus DET, and bulky groups. All the reagents involve bulky groups because it provides excellent selectivity during the synthesis. Allylic alcohol, everyone knows, 3 carbon with alkene, tertiary butyl hydroperoxide, that is peroxide with tertiary butyl group. It can be mentioned as TBHP, BuOOH. Titanium isopropoxide means titanium with 3 oxygen with propyl groups, plus DET and minus DET. Plus DET means both R groups alcohol below the plane. Minus DET means alcohol above the plane, 2S configuration. So you should master the reagent to master the synthesis. The mechanism is very complicated, often debated by many people. You can simply understand the mechanism. Alkene is attacked by DET. It can be from minus DET or plus DET. Plus DET from Re phase attack or below the plane attack. Minus DET mean above the plane attack. Here alcohol position also important. So through the help of titanium isopropoxide and peroxide, you have above the plane epoxide or below the plane epoxide. Mechanism is very complicated. I mentioned as simple as that. Here crucial part is DET and alcohol. We will see that in upcoming slides. The most important thing you should learn is OH position and DET. Here first step you should bring alkene vertical and alcohol above. So bring the double bond vertical. Rotate the alcohol to the top side. Then you decide whether alcohol is left side or right side. So alcohol left or right is the real data here. Then DET nature also important. Whether it is plus DET or minus DET, decide the product. Here I given the matrix table, plus DET minus DET, alcohol right side, alcohol left side. Plus DET, alcohol right mean above the plane epoxide, OH left mean below the plane epoxide, minus DET, OH right mean below the plane epoxide, OH left mean above the plane epoxide. Better you memorize this table to avoid the confusion. Then trick to memorize this table. Here OH position and DET is important. To memorize this, here I given the acronym PARA. PARA mean plus DET, alcohol right side mean above the plane epoxide. So memorize the word PARA, write the first column, then enter the other possibilities with reverse configuration. So PARA mean plus DET, alcohol right side above the plane. This is a very important trick. It will help you to solve all the problems. Here the common mistake everyone make, position of alcohol. We should bring OH above, double bond vertical. Here I shown 4 different orientation of the same compound. To analyze the final product, you should bring alkene above, top of the paper. You should bring alkene vertical and OH on the top of the paper. If you bring OH down, even with alkene vertical, it is wrong. If you bring OH above, but double bond is horizontal, mean it is wrong. The double bond horizontal in the left side also wrong. So best one is double bond vertical, alcohol on top of the paper. Next basics is regioselectivity. Suppose you have two alkene in the system which will get into the epoxide. Here I shown the example. One it has allylic alkene, another is side chain alkene which will react. Since both are alkene, the concept involved is regioselectivity. Here OH act like an anchor. Here OH is the functional group, act like an anchor. So allylic alkene reacts, not the isolated alkene. So the concept we have to learn here is only allylic alkene reacts, not the isolated alkene. Then the interesting basic. What will happen if there is any other chiral center in the reaction? Since the reaction involves too much stereochemistry, there can be a doubt that other chiral centers also involved affect the final product. But other chiral centers are not disturbed. No change in the configuration happened. Only epoxidation happened diastereoselectively. Final product is epoxide according to DET and alcohol position. So retention of configuration happened without any change in the chiral center. Then you should master the stereochemistry to solve the problems. Why? Here I given the starting material with geometry, different perspective, methyl and ethylene alcohol above the plane and methane, ethane below the plane. By looking at it, you may get confused. If you see through the bisection, it is just a simple compound, both are same. It will avoid the confusion and simplify the process. So master the stereochemistry. This is the very basic and simple one. You should always focus on functional group because alkene and alcohol is the reaction center. All others are distracting. So simply give the name R and do the reaction to avoid the confusion. It will give better clarity to the reaction. Then we are going into the next section, 25 fully solved examples. You may wonder why so many examples, because problems are best way to learn. It will give different perspective and complete understanding. So solve the problem, master the concept. Let us see the first example. Here you have linear compound with cisalkene and transalkene. Allylic alkene is cisalkene, terminal alkene is transalkene, and you have terminal alcohol. You are using plus DET, titanium isopropoxide, tertiary butyl peroxide, dichloromethane. You should find what will be the final product. By looking at the allylic alcohol and plus TET, you might realize it's a Sharpless Asymmetric Epoxidation. So let us go step by step. Here you have two alkene, but only allylic alkene reacts. That is regioselectivity. So bring the alkene vertical, OH above. If you look at it, OH is on left side, alkene is vertical. We are using plus DET. If you look at the table, plus DET, OH left side mean below the plane epoxide. So you draw the oxygen below the plane, find the final product. The concept you have to learn here is only you have to look at plus TET and OH group to identify the final product. Then the next example. Here you have dialkene system. The compound position vertically, not linearly. You have terminal alcohol, 3-methyl group. You are using -DET, titanium isopropoxide, tertiary butyl hydroxide, dichloromethane. You should find what will be the final product. Here, by looking at the alkene and alcohol DET, you might realize it is a Sharpless Asymmetric Epoxidation reaction. So, we have to analyze position of OH, position of alkene and DET. DET is -DET. We only analyze alcohol. To find the alcohol, bring the alkene vertical and OH above. If you bring it, you can clearly see OH is on left side. So OH left side -DET mean if you look at the table, it is above the plane epoxide. So only allylic alkene reacts. Above the plane epoxide mean you should position the oxygen above the plane. So the concept you outline here is even with complicated molecule, analyze the alkene with basics, bring the alkene vertical, OH top of the plane. Then the next question, here you have cyclohexane. First position you have exocyclic double bond with alcohol. You have 2-methyl group. You are using -DET as the reagent and titanium isopropoxide, then tertiary butyl peroxide. You should find what will be the final product. Here you should identify whether it will go Sharpless reaction or not. Here you have allylic alcohol. You should know that exocyclic double bond with third carbon alcohol and -DET mean Sharpless asymmetric epoxidation is an enantioselective reaction or diastereoselective reaction. Straightforward, we get into the problem. Here you have -DET. Let us analyze the OH position. Here double bond is already vertical, OH on left side. So -DET, OH left side means above the plane epoxide. So you should position the oxygen above the plane. You find the final product. This problem insists on the fact that you should identify the allylic position and allylic alcohol to get involved in the Sharpless asymmetric epoxidation. Then the next example, here you have cyclohexanone. Second position you have dimethyl group. You are using phosphine ester and carbonyl ester, then sodium hydride and lithium aluminum hydride, DDET, tertiary butyl peroxide, titanium isopropoxide. You should find what will be the final product. This example will help you to learn Sharpless reaction can be a part of big molecule synthesis. Let us go by the basics and reagent. Here you have ketone, which is carbonyl group, and you have phosphine halide. You are using sodium hydride and phosphine oxide. Here you have active methylene group. Hydrogen is acidic. It can be removed. It forms nucleophile, which is halide. It attacks the carbonate. You have new CC bond. Then phosphine oxide bond form because phosphorus has high affinity towards oxygen. 4-member ring form. Phosphine oxide eliminates. You have conjugated ester. Here you have E-alkene. Why? Because halide is stable halide. So E-alkene form. Then you are using lithium aluminum hydride, which converts ester into alcohol, which is allylic alcohol. Since you are using diethyl tartrate, allylic alcohol is there mean Sharpless asymmetric epoxidation. It is a diastereoselective reaction. So we go by the basics. -DET, alcohol left side mean you have above the plane epoxidation. So you end up with epoxide above the plane. The concept you outline here is You should master all the naming reaction, then only you can identify final product in big molecule synthesis. Then the next question. Here you have alkene. It has 4 attachments. One side with methylene alcohol, 2 methyl group, and you have side chain alkyl group which is C8H17. You are using peroxide in butyl form, 4 molar of titanium isopropoxide, 2 mole of DET and dichloromethane in minus 10 degrees Celsius temperature. You should find what will be the final product. Here you have alkene which contain alcohol, that is allylic alcohol. So Sharpless Asymmetric Epoxidation. So we go by the basics. We find the OH position, bring the double bond vertical and OH above. Then you can find OH is on left side. Then you are using plus DET. So plus DET, OH on left side mean below the plane epoxidation. So the concept you have to learn here is always analyze the position of OH carefully. You should bring OH above double bond vertical to identify the correct configuration. Then the next question. Here you have alkene vertically positioned. You have alcohol, isopropyl group and trans hydrogen. You are using peroxide in tertiary butyl form plus TET, titanium isopropoxide. You should find what will be the final product. Here you have alkene and alcohol. Alcohol is the allylic alcohol. You are using the tertiary butoxide and DET mean Sharpless Asymmetric Epoxidation. So we will go by step to identify the product. First we find the position of OH. To find the OH, bring the alkene vertical and rotate the OH to the top side. If you find it, OH is on left side. You are using the plus DET. According to this table, epoxide form below the plane. So draw the oxygen below the plane. That is our final product. The concept you have to learn here is, however the structure can be twisted, you should redraw the alkene to find the position of OH. Then the next example. Here you have linear chain compound with alkene and alkyne and alcohol, 2 methyl groups at terminal, alcohol also at terminal. You are using the lithium aluminum hydride plus TET, titanium isopropoxide. You should find what will be the final product. The reaction involves extra one step. You have to reduce the alkyne into alkene. Lithium aluminum hydride selective to allylic reduction. So allylic triple bond got reduced to the trans form. You got trans alkene. If you are interested, go and study separately. It is a regioselective reduction, or you can call chemoselective, because both are different functional groups. Finally, we got the required compound, which is allylic alcohol. If you find the position of OH, its left side, plus TET you are using in below the plane epoxide. So our final product is epoxidation happen below the plane. The concept you have to learn here is Sharpless reaction can be a part of the large molecule synthesis or multi-step synthesis. Then the next example. Here you have alkene. One terminal you have methylene alcohol. Other terminal you have propyl group. You are using peroxide with tertiary butyl bulky group minus DET, titanium isopropoxide. You should find what will be the final product. Here you have allylic alcohol, peroxide minus DET, titanium isopropoxide mean Sharpless Asymmetric Epoxidation. So allylic alcohol, position of OH is important. Double bond is already vertical. OH is on left side. You are using minus DET. According to the table, if you see minus DET, OH left side mean epoxide above the plane. So final product is oxidation happen above the plane. The concept you have to learn here is sometimes solutions are obvious, but most of the time you should identify the position of OH as well as influence of TET. Then the next example, you have cyclohexene, side chain you have alcohol, peroxide in tertiary butyl form you are using, minus DET, titanium isopropoxide you are using. You should find what will be the final product. Here alkene is there, alcohol is there, it is allylic alcohol. So chances of asymmetric epoxidation. DET also confirm the epoxidation. So we should go by step. First we will see position of alcohol. Double bond is already vertical. Alcohol is on right side. Minus DET you are using. So if you look at the table, minus DET, alcohol right side mean below the plane epoxide. So you should draw oxygen below the plane. The concept you outline here is identifying allylic alcohol is important in the macrocyclic system. Then the next example, you have fluorobenzene. Third position you have allylic alcohol attachment. Tertiary butyl peroxide you are using, minus TET, titanium isopropoxide as a reagent. You should find what will be the final product. Here you have allylic alcohol, peroxide and DET isopropoxide you are using. So chances of Sharpless asymmetric epoxidation. We will go by step. First step will be position of OH. To find the position of OH, you should bring double bond vertical. Here it is a big system. So rotate the alkene, bring the vertical and bring the OH above. If you look at it, OH is on left side. OH left side minus DET you are using mean according to the table minus DET OH left side above the plane epoxide. So you should draw epoxide above the plane. The concept you have to learn here is whenever you are solving problem with bigger molecules, you should stick with fundamentals, only focus on functional group, identify the final product. Then the next example, here you have linear compound, it is alcohol with 2 cis alkene and side alkyl group. You are using tertiary butyl peroxide minus DIPT, titanium isopropoxide. You should find what will be the final product. Here you have 2 alkene. As we seen already, alkene near the alcohol reacts. So it's a regioselectivity. Among the 2 alkene, allylic position alkene reacts. So you have peroxide, DIPT mean chances of Sharpless asymmetric epoxidation. So we go with our understanding. First we analyze position of OH. For that you should bring double bond vertical, OH above. If you do it, you can see OH is on left side. You are using minus DIPT. So if you look at the table, position of epoxide is above the plane. So you should draw the epoxide above the plane. The concept you outline here is if you have 2 alkene, only allylic alkene reacts because Sharpless reaction is regioselective. Then the next example, here you have chiral carbon, one attachment is cyclohexane, below the plane hydrogen, alcohol and allyl group. You are using tertiary butyl hydroxide minus DET, titanium isopropoxide. You should find what will be the final product. Here you have chiral compound, but our interest is enantioselective synthesis. So we focus on allylic alcohol. So allylic alcohol minus DET. So Sharpless asymmetric epoxidation is possible. For that we should find position of OH. So at first we will see where the OH is placed. So you should bring double bond vertical OH above mean. You can clearly see OH is on left side. So OH left side minus DET you are using mean above the plane epoxide. So you should draw oxygen above the plane. Why this problem is important? Here you have another chiral center. It is not disturbed at all. It is a retention of configuration. Even though it is near to reaction center, it is not disturbed. So the concept you have to learn here is in Sharpless epoxidation, other chiral centers are not disturbed. Then the next question. Here you have alkene. Two methyl groups are trans to each other and one ethyl and methylene alcohol are trans to each other. All are clearly specified with stereochemistry. You are using tertiary butyl peroxide minus DET, titanium isopropoxide. You should find what will be the final product. The starting metal is twisted, so we draw a simple geometry, avoid the stereochemistry, look from different perspective, redraw the plane of bibond, clearly see allylic alcohol. You are using minus DET, so chances of asymmetric epoxidation. So first step will be finding the position of OH. If you bring double bond vertical, OH is on left side, OH above, you can clearly see OH is on left side. OH is left side. You are using minus DET. So if you look at the table, you can clearly see above the plane epoxide. So alkene oxidized to above the plane epoxide. The concept you have to learn here is you should master the stereochemistry to avoid the confusion in the product identification. Then the next example. Here you have linear chain compound with two trans alkene, two methyl group, one OH. You are using titanium isopropoxide, tertiary butyl peroxide, L plus DET. You should find what will be the final product. Here you have allylic alcohol minus DET you are using. So the chances of Sharpless asymmetric epoxidation. But one twist is here you have two alkene, but our reaction is regioselective. Only allylic position alkene is reactive. So we focus on allylic alkene. First step will be identifying the position of OH. So bring the double bond vertical, OH above mean. You can see OH is on left side. Plus TET you are using. OH is on left side mean below the plane epoxidation. So you draw the oxygen below the plane and identify the final product. Here the concept you have to learn here is Sharpless asymmetric reaction is regioselective. Only alkene in the allylic position reacts. On the contrary, isolated alkene don't involve in the Sharpless asymmetric epoxidation. Then the next example. Here you have alkene. One side methylene alcohol, another side methyl group. You are using titanium isopropoxide, tertiary butyl peroxide, D minus DET. You should find what will be the final product. Here you have allylic alcohol, DET you are using. Straight away you can guess that it is Sharpless asymmetric epoxidation. First step will be identifying the position of OH. For that you should bring double bond vertical OH above. If you bring it, you can clearly see OH is on left side. So OH left side minus DET. So above the plane epoxide. So you should draw oxygen above the plane. The concept you have to learn here is always stick with fundamental to identify the final product. Then the next example, you have alkene, one side methyl group, transposition you have methylene alcohol, titanium isopropoxide you are using, tertiary butyl hydroxide plus DET you are using. You should find what will be the final product. Here you have alkene, alcohol in allylic position. You are using plus DET. So chances of Sharpless asymmetric epoxidation. To identify the product, you should find position of the OH. To find the position of OH, you should bring double bond vertical OH above. Then you can clearly see OH is on left side. OH left side plus TET you are using mean below the plane epoxide. So you should draw the oxygen below the plane. The concept you have to learn here is the position of OH may be twisted. Always you focus on fundamental. Redraw the molecule to alkene. So redraw the alkene to the vertical. OH on above. Then the next question, you have benzene. Side chain you have alkene with methylene alcohol. You are using titanium isopropoxide, tertiary butyl peroxide and plus DET. You should find what will be the final product. Here alkene in the side chain, but it is allylic alcohol. You are using the DET. So chances of Sharpless asymmetric epoxidation. So first step will be identifying the position of OH. So bring the double bond vertical. OH above. You can clearly see OH is on left side. OH left side plus DET you are using. So below the plane epoxide. If you draw oxygen below the plane, you have final product. The concept you have to learn here is you should focus always on reaction center, not the side chain bulky molecules. Then the next example. Here you have ether, one side ethyl group, another side long chain with alkene and alcohol. You are using titanium isopropoxide, tertiary butyl peroxide plus DET you are using. You should find what will be the final product. Here you have alcohol, ether and alkene, but alcohol is allylic alcohol with DET mean chances of Sharpless asymmetric epoxidation. So first step will be as usual identifying the position of OH. For that you should bring double bond vertical OH above. If you do that, you can clearly see OH is on left side. Plus DET you are using. So OH left side plus DET below the plane epoxidation. So draw the oxygen below the plane. The concept you have to learn here is chemoselectivity. Only allylic oxygen reacts. Only allylic alcohol reacts, not the ether. Then the next question. Here you have heterocyclic compound with 2 oxygen, 2 methyl group. Side chain you have alkene with alcohol. You are using titanium isopropoxide, tertiary butyl peroxide minus DIPT. You should find what will be the final product. Here molecule may be bigger. We stick with our focus that alkene and alcohol minus DIPT. So chances of asymmetric epoxidation. First step will be finding the position of OH. So we bring the double bond vertical, rotate the molecule, position OH above. If you do that, you can clearly see OH is on left side. Minus DIPT you are using. OH left side minus DIPT mean above the plane epoxide. So draw the oxygen above the plane. You have the final product. The concept you have to learn here is always focus on the functional group, reduce the distraction and identify the final product. Then the next example. Here you have alkene. One side you have methylene alcohol. Another side you have long chain. You are using titanium isopropoxide, tertiary butyl hydroxide minus DET. Second step you are using PCC DCM. Third step phosphine halide. you should find what will be the final product. The reaction involved multi-step synthesis. We will go by our understanding. So long chain we reduce to the R group. So simplified allylic alcohol, titanium isopropoxide you are using, minus DET, OH is on left side mean, below the plane epoxide. So it is a typical Sharpless asymmetric epoxidation. Next step you are using PCC and DCM. PCC is an oxidizing agent, selective to alcohol, convert alcohol into carbonyl, here aldehyde. Next step phosphine halide you are using. Phosphine and carbonyl gives alkene there. So you have final product with definite geometry. The concept you have to learn here is Sharpless asymmetric epoxidation can be a part of big molecule synthesis. Then the next example, here you have benzene, amine with protecting group, second position, that is ortho position, you have cisalkene with alcohol, titanium isopropoxide you are using, tetrabutyl peroxide, minus DIPT as a reagent. You should find what will be the final product. Here you have allylic alcohol, DIPT you are using. So chances of Sharpless asymmetric epoxidation. So we focus only on functional group. First step will be finding the position of OH. So we bring the alkene vertical, OH above. If you do that, you can clearly see OH is on right side. So OH right side minus DIPT below the plane epoxidation. So draw the oxygen below the plane. You have the final product. The concept you have to learn here is there will be a many functional group, but you should focus on reaction center. Then the next example, here you have alkene, one side with alkyl group, another side methylene alcohol, both are cis to each other. Titanium isopropoxide you are using, tertiary butyl peroxide, and two different pathway with two different DET, minus DET and plus DET. You should find what difference it can make in the final product. Here answer is simple. Here you have allylic alcohol, minus and plus DET control the reaction. So Sharpless asymmetric epoxidation. First step, you should find the position of OH. So bring the double bond vertical, OH above. If you do that, you can clearly see OH is on left side. If you use plus DET, epoxidation happen below the plane. If you use minus DET, epoxidation happen above the plane. So two different reagent, two different product, all are stereochemically controlled. The concept you have to learn here is this problem giving the clear indication is that DET is the controlling reagent, dictate the final product. Then the next question, you have alkene, one side you have trimethyl silyl group, another side you have methylene alcohol. You are using titanium isopropoxide, tertiary butyl peroxide minus DET. You should find what will be the final product. Here the reaction may give little confusion because it has silyl. As we discussed already, we focus on functional group. Here you have alkene and alcohol, which is allylic alcohol. DET you are using. So Sharpless asymmetric epoxidation. First step will be identifying the position of OH group. Bring the double bond vertical, OH above. If you do that, you can clearly see OH is on left side, minus DET you are using. OH is on left side mean above the plane epoxidation. So draw the oxygen above the plane, that is your final product. The concept you have to learn here is other functional group like silicon don't interfere with Sharpless asymmetric epoxidation. Then the next example, starting material is cyclohexene. Side chain you have methylene alcohol, titanium isopropoxide you are using, tertiary butyl peroxide as a reagent, and DET. You should find what will be the final product. Here alkene is there, alcohol is there, so you should identify the allylic position. Yes, it is allylic alcohol plus TET you are using. So Sharpless Asymmetric Epoxidation. First step will be finding the position of OH. For that you should rotate the molecule to bring the alkene vertical, OH above. If you do that, you can clearly see OH is on right side, OH right side plus TET. So epoxidation above the plane. So draw the oxygen above the plane. You have the final product. The concept you have to learn here is alkene can be a part of the ring, but we go with fundamentals and find the product. Then the final example. Here you have alkene. One side you have methylene alcohol. Another side you have ester. Titanium isopropoxide you are using. TPHB as the reagent and plus DIPT. You should find what will be the final product. Here there are three functional groups, alkene, alcohol and ester. Our interest is alkene and alcohol, that is allylic alcohol. DIPT you are using. So chances of Sharpless asymmetric epoxidation. First step will be finding the position of OH. So bring the double bond vertical, OH above. If you do that, you can clearly see OH is on left side. So OH left side plus DIPT you are using. So below the plane epoxidation. So draw the oxygen below the plane. That is your final product. The concept you outline here is, even though many functional groups present in the system, only allylic alkene and alcohol reacts, you have the final product. Then let us summarize what we learned. First you should memorize the table, whether you are having reagent plus DET or minus DET and position of OH left side or right side. If you do that, you have the table and you can clearly identify the final product. The trick will be para plus TET mean alcohol, right side above the plane epoxide. The acronym is para. The remaining possibilities do the reverse. Then important thing is bring the OH above with double bond in the vertical position. Then another important thing is only allylic alkene reacts, not the isolated alkene.